Hi, my name is Jawad from Singapore Polytechnic. Our team, RoboErectus, is excited to be participating in the RoboCup Asia Pacific in Qingdao, China. From left to right, the RoboErectus team consists of Sarah, me, Sam, and Joel. And together, we'll be presenting the innovative algorithms and strategies we have integrated into our robot for this competition. The main challenge for ADL in the university category is to complete Task 2. In this task, the robot starts with 6 packages and delivers them to the designated stations, returning to the distribution center to reload when necessary. During loading or delivering, the robot must remain stationary for 2 seconds, with its LED light flashing red and yellow alternatively. Each package is assigned to a specific delivery station with deadlines and scores based on color. Red indicating critical urgency with the highest score of 90, followed by orange, yellow, and green. Deadlines start as the game begins, as the score decreases over time except for green packages. If not delivered on time, the score for red, orange, and yellow parcels drop to a minimum of 10, indicating expiration. During this video, we will be using this map as shown for any demonstrations. For Task 2, our objective is first to ensure a smooth navigation through delivery and collection stations, as well as navigation points, and second, to maximize our score using the most efficient approach possible. Our strategies include Dijkstra's algorithm, which efficiently computes the shortest paths between nodes in a graph, ensuring that each node is connected to every other node with the minimal possible distance. In addition to this, we employ a brute force method that considers parser deadlines and scores, evaluating every possible delivery route to identify the most optimal combination of delivery points. To ensure accurate navigation, we also utilize a PID controller, which keeps our robot on track within the road boundaries and follow the center line. Let's explore how Dijkstra's algorithm is implemented in detail. For the Dijkstra algorithm, we start by selecting a node as a starting point, setting its distance to 0 while initializing all other nodes with a distance of infinity. We then visit the nearest unvisited node, updating the distances to its neighboring nodes and marking it as visited. After reaching the designation, we trace back to the starting node using the recorded distances. This process is repeated for all nodes, ensuring that we compute the shortest path between every pair of nodes. For brute force approach, we begin by generating all possible route combinations using permutations. Next, we calculate the total distances for each permutation. We then compare these routes based on their total distances and select the one with the shortest distance as our optimal delivery route. Lastly, we implemented PID line tracking to help our robot stay on course by adjusting its steering based on sensor feedback. The PID controller reduces error by using proportional, integral, and derivative adjustments, ensuring smooth and precise navigation for accurate line following.
Here are the results before and after implementing our strategies. On the left, you can see the final score of the robot using manual routing, while on the right, the score reflects the robot's performance with our optimized strategies. The outcome showed significant improvement with an increase of about 100 points. The PID controller ensured the robot stayed centered throughout the run, and a combination of Dijkstra's algorithm and the brute force method identified the most optimal and efficient routes from point to point during the game. This gameplay showcases our robot implementing the strategies we have discussed. As you can see, it effectively calculates points and distances, assessing the value of each delivery. Consequently, it also reacts by prioritizing deliveries to the centers that generate the most points in the shortest amount of time. The challenges our team faced while coding included improving the PID controller, optimizing the robot station distances, and digitizing the map. To keep the robot on track, especially after turns, we added an integral limit to prevent wind-up, which allowed for faster and more accurate course corrections. Optimizing the distances between delivery, collection stations, and navigation points was a challenge, as it required numerous tests and parameter adjustments to find the optimal values. Lastly, digitizing the map was tricky since we manually entered coordinates. To ensure consistency, we created a points coordinator to align points that shared the same line with identical X or Y values. The controller parameters KP, KI, and KD are adjusted after each run for optimal performance. The proportional P component measures the difference between the robot's actual and desired positions, applying a correction based on this error. The integral I component accumulates past errors to eliminate persistent steady-state issues caused by external factors, while its constraints prevent wind-up, ensuring stability and smooth travel, especially after turns. Lastly, the derivative D component predicts future error trends, allowing the robot to anticipate overshoot and oscillations, facilitating smoother movement. Through our preparation for this competition, we have gained valuable insights. One key lesson was the importance of clear communication and effective collaboration within the team. We learned to understand each member's strengths, allowing us to allocate tasks more efficiently and achieve better results. Additionally, we developed critical thinking and adaptability, crucial for quick decision-making and risk assessment, especially since the maps are dynamic. This helped us to respond quickly and deliver complete functional code under the tight time constraints during the competition. By integrating real-time route optimization algorithms and deploying autonomous vehicles, we have the potential to dramatically increase efficiency and logistics through optimized delivery routes that save fuel and time, enhance traffic flow by monitoring real-time data, and adjusting signals to reduce congestions, and improve public services by automating waste collection, road maintenance, and infrastructure inspections. Thank you for listening.